Welcome to the Yvonne Brill Lecture in Aerospace Engineering.
Well, if you were thinking of taking your after-the-lunch nap, that should have snapped you out of it. But what a great time to be an engineer. We all work to solve some of the biggest issues facing our planet, like the energy transition to net zero carbon. And we're exploring some of the greatest mysteries that lay beyond our planet in space. Well, good afternoon. I'm Al Romig, the Executive Officer of the National Academy of Engineering, and proud member of the NAE Aerospace section, and also a fellow of the American Institute of Aeronautics and Astronautics. So on behalf of AIAA and the NAE, I am pleased to open the Yvonne C. Brill Lectureship in Aerospace Engineering. Welcome. The Brill Lectureship in Aerospace Engineering was established in 2013 in memory of Yvonne Brill, a rocket scientist who was both an AIAA Honorary Fellow and an NAE member. She was a trailblazer at a time when women were not encouraged to enter the fields of science and technology. She truly embraced the spirit of AIAA. It is obvious that she shaped the future of aerospace through the invention of a revolutionary propulsion system, the hydrazine-resisted jet propulsion system, that remains the industry standard for geostationary satellite station keeping. Yvonne also shaped the future of aerospace for women. She was an active voice for women in science and engineering, helping ignite the understanding that one's gender has no bearing on one's ability. She was a pioneer in a male-dominated profession at a time when it was common to think women were unable to tackle the hard problems our community regularly solves. This lectureship, named for her incredible contributions, emphasizes research or engineering issues for space travel and exploration, aerospace education of students and the public, and other aerospace issues such as ensuring a diverse and robust engineering community. With me today is John Cassani to introduce the lectureship awardee. John?
Thank you, Al. I just said thank you, Al. So this is a great day for us. Yvonne Brill was an amazing woman. Al gave you quite a bit of a rundown on her. I had some personal relationships with her. She helped not only women, but she helped men too. I think when she was early in her career, she was married and had 3 kids and had been working very, very difficult job, and wasn't able to do both of those, do a good job of both of those working full time. So she took a job working part time for 6 or 8 years and used that time to raise her kids. And she once, one quote I remember hearing from her was that it's harder to get a good husband than to get a good job. So, but in her case, I think the fact that she had kids made her not only look to helping women, but she also helped young people of every gender. And I was one of them, and I'm very grateful for the help I got from her as a young guy in the NAE. Anyway, that's all I want to say now. I want to welcome our guest speaker, who is Bobby Braun. Bobby had more than 35 years' experience as a space systems, in space systems, as an engineer, technologist, and organizational leader. He has contributed to the formulation, development, and operation of multiple spaceflight systems and missions, and is a recognized authority in hypersonics technology and the development, entry, descent, and landing. I've worked on several projects at JPL, all of the Mars missions, and in particular, one mission, which was the Galileo mission, which involved sending a probe from the spacecraft into the atmosphere of Jupiter. And entry velocity, I think, was 25,000 miles an hour or something, higher than that, Bobby's telling me. And Bobby was key to that development and many more Mars landing missions. Dr. Braun, wait a second. Previously served as director of JPL. He was not exactly my boss, but he could have been. I had great admiration for him. He was at JPL for about 5 years. He was, and he had also been the dean of the College of Engineering Applied Sciences at Colorado Boulder, a faculty member of Georgia Tech, and a member of the technical staff at NASA Langley Center. In 2010, Dr. Braun received the first NASA Chief Technologist, served as the first NASA Chief Technologist for more than a decade. In this capacity, he was responsible for the development of the agency's technology and innovative policy and programs. He created and led the initial implementation of a spectrum of the NASA technology programs designed to build the capability required for our nation's future space missions. This activity spanned 10 NASA centers, industry, academia, and fostered partnerships between NASA and other government agencies. Dr. Braun's a member of the NAE and a fellow of the AIAA. He is the author or co-author of over 300 papers. So it is my distinct pleasure to introduce Bobby to present this lecture titled, Are We Alone? Grand Challenges in the Solar System Exploration. Bobby?
Hey, John. Thank you, sir. I appreciate it.
You're welcome.
It's great to see you.
You just thanked me for that clumsy introduction.
I did. It was great. Appreciate it, John. Thank you all. And thank you for the honor of having the chance to speak with you here today. Before I get started, I just wanted to make a couple points. First of all, this lecture is very special to me. I'm a student of aerospace, and there have been so many giants in the field of aerospace. And when I was coming up, I was trying to decide, was I going to be a flight dynamics person or was I going to be a propulsion person? And the way I decided is I would go to as many of the AIAA conferences as I could. So every year I'd go to the Flight Mechanics Conference, and every year I'd go to the Joint Propulsion Conference. And at one of the first Joint Propulsion Conferences that I attended in the late 80s, I met Yvonne Brill. And I knew she was speaking, and she was a luminary in the field, and so I actually went to her talk, which was fascinating. And I tracked her down afterwards so that we could talk for just a few minutes. She was very giving of her time and very helpful to a young person who was coming up in the field. I ran into her again many years later when she was awarded the National Medal for Technology and Innovation by President Obama in 2010-2011 timeframe. And if there's anybody who deserved that award, Yvonne certainly did. So to be able to give this lecture in her name is very special to me, and I appreciate the nomination and folks that put this forward. Secondly, I'm going to be talking about this topic, but we had a major event in the space community just 8 days ago. At the Applied Physics Laboratory in the control room, we managed the DART spacecraft as we did the first planetary defense test mission. For the first time, humanity actually moved a celestial object in a significant enough way that we can measure that deflection. And I know a number of members of the DART team are watching online right now from APL, from JPL, from Goddard, from across the country. And if you wouldn't mind, I'd like to give the DART team a round of applause for their time. Okay, so are we alone? It's a pretty weighty topic. I will admit to you up front, this is a topic that I am not an expert in, but one that has fascinated me for most of my adult life. And so given this opportunity, it was something that I wanted to talk about with this group. For as long as humankind has walked this earth, we've looked up at the night sky. And perhaps, like many of you here today, I can remember the first time, I grew up near the city, and I can remember for perhaps the first time when I went to camp up in the mountains, and I had that clear, unobscured view of the sky. And it looked something like this, not exactly, but I remember thinking, it was just remarkable because it was so different from a mountain view than what you would see every day because of light pollution, in the city. And it was just clear. There were so many stars in the sky. And each of those stars, of course, is a sun. But when I was a kid, we knew from grade school that there were 9 planets. And there were exactly 9. Pluto was included as a planet, by the way. But there were 9 planets, no more. And so you were left to wonder, what's out there? I grew up on Star Trek and science fiction books, movies like Star Wars. And, when I was searching my thoughts would drift into those worlds. And so years later, when I went off to college and I had the opportunity to study engineering, I never dreamed that I'd actually get to work in the space field. And I get to work every day with scientists and engineers from around the world on some pretty fascinating challenges, most of which have been focused on answering fundamental questions, like, are we alone? Now, some folks will try to divide scientists from engineers. There's a famous quote attributed to von Karman that says, scientists discover the world in which we live, but engineers create the world of the future. I find that to be an artificial divide. In my own career, the activities that I'm most proud of are when scientists and engineers, and frankly, folks from all walks of life, have worked together on teams to go after some pretty amazing challenges. And if you think about the question, are we alone? Every time we take a step towards answering that question, it's not an individual, it's not a scientist or an engineer that answers that question, it's a team. It's a team sport. And so, for example, space science, which is the field that we'll be talking about today, it's dramatically altered our understanding of our own place in the universe. Not just what's happening today, but if you go back into the past. Of course, early in our society, very early in civilization, we knew that we were the center of the universe. It had to be so because the moon and the sun rose in the east and set in the west, revolving around us. And that view of our world, with humankind and the earth in the center, was the mode that humans thought about for many centuries. And what did it take? It took Galileo to break us of that mode with new technology, the telescope, right? And in 1609, Galileo, using his telescope, observed, and you can see in the upper left image here, observed the 4 largest moons of Jupiter revolving around that planet. And that was a model for solar system dynamics. He thought, well, perhaps if these small bodies are revolving around the larger one, the sun's much larger than the Earth, perhaps the Earth is rotating around the sun, revolving around the sun as well. And that, along with some other work, led to the Copernican revolution. Fast forward a few centuries, in 1923, Edwin Hubble, using a new technique to determine the range to a pulsating star, V1 in the Andromeda galaxy, proved that there was more than one galaxy, that we humans weren't just in the only solar system, in the only galaxy in the universe, but that there were many galaxies. Fast forward a couple decades to 1990 in the era of spaceflight, right? And you have Voyager 1 in the upper right image there, turning back towards the Earth from a distance just beyond Neptune's orbit, and taking a picture, if you look very closely in the center of that image, that bright yet pale blue dot, that's us. That's every one of us. That's everyone that we know or have ever known, Carl Sagan said. That fragile world in the vastness of space is the Earth. And that's our abode. That's also, as far as we know today, the only place that life exists. When that image was taken in 1990, as I was saying, there were 9 known planets, and it was a well-known fact. But technology was still growing and evolving, and in the 2008 to 2020 timeframe, we flew the Kepler mission, a small, low-cost telescope that focused on a particular patch of the sky, and over a period of about a decade, identified not 1 or 100, but several thousand planets around other stars. In the blink of the eye, right, in the time of my professional career, I was already working in 1990 at NASA Langley Research Center. I had already met Yvonne Brill. In the blink of an eye, we went from 9 planets to thousands. And so what's ahead for us in the future? I can't tell you with certainty, but I can tell you that as we move forward in space science, what we know about ourselves and what we know about the world around us, to include the entire universe, will fundamentally shift. It'll shift in specific times like the ones listed here. But what do we know today? This is an image of the Earth taken by the Lunar Reconnaissance Orbiter, much closer than the Voyager 1 view of the Earth. It's a beautiful blue marble in the vastness of space. There's a juxtaposition about our own world. Today, the Earth is the only planet that we presently know of to harbor life. Not only does it harbor life, this one planet, but the Earth is teeming with life. It's almost impossible to go any place in the Earth, the deserts, the highest mountains, the deepest seas, and not find life. Microbial, single-celled life, variety of organisms. I'm not necessarily referring just to people, which, by the way, are everywhere now, but, to microbial life. It's all across the Earth. And so doesn't that make you wonder? If there's life in the highest mountains, in the deepest seas, and there are worlds in our own solar system that emulate those environments, what does that mean about life in our solar system? If there's not just 9 planets, but thousands, maybe tens of thousands, hundreds of thousands of planets, what does that tell you about the odds for life in those conditions? And so what I would hypothesize here today is that we're no different than those early generations of explorers. We know what we know. We're inventing technology to further our knowledge, and we feel the need constantly to explore this question. And as we do explore this question, our place in the universe will change yet again. Now, this work has been going on for many decades, and there's now a formal field of science called astrobiology. In fact, in the most recent National Academy's decadal survey for the planetary science discipline, it was actually called the Planetary Science and Astrobiology Decadal Survey. And astrobiology is not something that's just embedded within planetary science. It's actually a part of astrophysics and other disciplines of science as well. And broadly speaking, astrobiology is the study of life in the universe, and this is a rapidly growing field, both from a science and a technology point of view. It has a range of thrusts, and I've kind of listed them here, to include habitability, the search for habitable environments, as defined environments that have water, the chemical ingredients for life, and energy sources for life. The search or the understanding of prebiotic chemistry. What was the chemistry that existed from which life began? And of course, signs of life themselves, DNA or other signs of complex life. This is a field that's growing significantly, and I will tell you, this is a field that is poised to alter our view of the universe. The coming decade, in my view, is one of great promise for the search for life in our solar system, and also for the understanding of Earth-like worlds around other stars. And that's what we're going to focus on here today. The reason that there's such promise in this field is that the fundamental technologies, the foundational technologies that we need to have a significant advance have been developed and have been demonstrated. 10 years ago, 20 years ago, that was not the case. But it is the case today. And we also have examples today of systematic approaches for examining a very difficult problem like this one and making step-by-step advances on such systematic approaches. And I'm going to talk to you about a couple of those examples and how what we've learned from these other programs could apply to the search for life either in our solar system's ocean worlds or on Earth-like planets around other stars. So what I'm talking about is a fundamental question, right? Are we alone? It's a multi-generational quest. I never had the opportunity to speak with Galileo, but I imagine he thought about this at some level. I imagine, people that aren't even born today will think about this as they go into adulthood and begin their careers. So the question before us is, how does one tackle a multi-generational quest? And as an engineer, I will give you the answer, which is to treat it like a systems engineering problem and decompose that problem into a set of interconnected parts that are logically sequenced or arranged in time based on the technology that we have in hand to take the next step and based on what we know today. So don't go try to prove life on a particular body at a particular moment in time, but build towards that by taking fundamental steps. And if you think about all the work that NASA has done over the last 30 years, there are two programs that immediately come to mind where this principle has been applied excruciatingly well. And as a result, in those two domains, NASA has made tremendous progress. One is the Mars exploration program, and I'll talk mostly about that today. But the other is our series of great observatories, right? Including Hubble and JWST and soon to be Roman. If you think about them from a technology development or from a scientific understanding, as the technology has advanced, we've been able to ask and answer more and more significant scientific questions. And it's this marriage, if you will, between science and technology that has allowed us to push forward on these types of issues. Now, we also have examples of just swinging for the fences. And as John mentioned, I've worked on a lot of Mars missions, so one of my favorite missions I'm going to use as an example, and it's one that I had no part in, but it's the Viking missions. The Viking missions back in the 1970s included our first landers, Viking 1 and Viking 2, on another planet. When I say our, I mean the United States. It was the first time the United States landed on another planet, and that upper image is from the Viking 1 lander. The goal of these missions were to search for life on Mars. The prevailing opinion was that life was perhaps prevalent across Mars. And so we could land and dig in the soil and do some experiments and find life. Unfortunately, Mars is a much more barren world than had been thought prior to Viking. And so while we sent life detection instrumentation of that time to Mars, the results that came back, there were 3 different instruments, and they were contradictory, and I would argue inconclusive. Carl Sagan said, extraordinary claims require extraordinary evidence. And the Viking landers, while hugely successful in showing Mars as a world of its own, a world deserving of study, did not conclude that there was life on Mars. And so what happened is we turned our back on Mars. We swung for the fences, and I would argue we struck out. And we chose, as a country, not to return to Mars for some 20 years. When we did, there was a young Miguel San Martin in the audience there, and a very young Bobby Braun, a part of that team that landed the Sojourner rover on the Mars surface, along with many, many others. Now, by the way, there's a fundamental difference between the Mars Pathfinder mission and Viking, and that's that we took a rover with us, right? We brought along mobility, something Viking didn't have. That technology didn't exist at the time. And after Mars Pathfinder, shortly thereafter, Mars Global Surveyor and Orbiter got into orbit about Mars, and we began a systematic study of the planet Mars. That systematic study was organized scientifically around themes, questions of life, climate, geology, and eventual human exploration. We organized our strategy for Mars exploration with a simple prioritization: follow the water. It's something we all understood. We're going to follow the water, search for water, and that will give us clues about habitable environments. That will give us clues about the climate history of Mars. That will give us clues about potential life on Mars. And over time, as our systems got more and more sophisticated, we moved from follow the water to the search for habitable environments to the search for signs of life in a very systematic way over 25 years. And in that time, we've learned a great deal about Mars as a potential abode for past life. And we've also learned a great deal about our own Earth, because Mars is an excellent analog for the early Earth, and its history has not been wiped away by earthquakes and tidal waves and oceans that we have on the Earth. And so when we look at Mars, in many ways, we're looking at an ancient Earth. So the Mars program, I would argue, has been remarkably successful. It's taught us about Mars, and it's also taught us about our home planet. In fact, in those 25 years, the U.S. has successfully flown 11 missions to Mars, a combination of orbiters and landers that have told us about the history of water and the habitable environments on Mars, to today, where we have multiple rovers in very different regions of Mars, teaching us about habitable environments and preparing for an even grander adventure. The U.S. program, with its 11 successful missions, has spawned partnerships with international partners, and in some cases, these other countries have begun to go to explore Mars on their own. Just this past year, in the United Arab Emirates, a couple years ago, sent the HOPE mission to Mars. And also in 2020, the Chinese had their first successful orbiter, lander, and rover, all in one package, successfully operate on Mars. The Europeans have been at Mars for some years now with the ExoMars Trace orbiter. They've also partnered on many of the US programs. And today, we are in partnership, NASA and the European Space Agency, with the next steps in Mars exploration, which is Mars sample return. And I'll talk about that in just a moment. But before I leave this chart, compare this statistic and this progress with Viking, going for a home run versus going for a single and then another single and then maybe a double and then another single, right? 25 years, we've learned a lot on Mars, and we're not done learning yet. Now, how did we do that? How did we send more and more capable systems to Mars? Well, technology was the answer. These systems, if you think about the Sojourner rover, it was about the size of a small baby. Spirit and Opportunity were about the size of a little golf cart that you might drive around. And of course, Curiosity and the Perseverance rovers that are presently operating on the Mars surface are the size of small cars. They're each about 1,000 kilograms, a little more than that even, and they have tremendous mobility features. So we have advanced our ability to land larger and larger things, entry, descent, and landing technologies. We can now land them much more accurately than we could, say, 10 years ago or 20 years ago. The systems that we're landing are much more complex scientifically. They have much greater mobility characteristics. They can actually go and interrogate some very difficult terrain and gather samples from regions of Mars that we could never have gotten to just a few decades ago. And we've really advanced sampling technology as well. Some of the missions have landed with scoops and shovels or drills. Others with cores. We have all kinds of ways of preparing the sample before it gets analyzed, either by powdering that sample or by heating it, for example. And so our science program at Mars is in full throttle. Now, before I leave this slide, I want to just point out one other thing. The hydrazine thruster has powered all of these missions in one way or another to the surface. And the hydrazine thruster, monopropellant thrusters, not only were they used in geosynchronous satellites and in rockets that traveled to the moon, but the Mars program is built on the electrothermal hydrazine thruster that Yvonne Brill originated. So she may not have been a part of these teams, but her legacy lives on in Mars. And this is the picture that I mentioned earlier with President Obama when she received the National Medal of Technology and Innovation. I mentioned Mars sample return, and this is a goal that the science community has been working towards for decades now, and we are there. Today, the Perseverance rover is traversing the Mars surface and gathering samples. It is gathering those samples up and sealing them in tubes, and those tubes will either be kept on the rover or some of them will be placed on the Mars surface for later pickup. While Perseverance is doing its operations on Mars, and by the way, about 15 tubes of the 43 that are on board have actually been sealed today. While Perseverance is doing its operations on Mars, we here on the Earth are building the next set of missions to go get that treasure trove and bring it back to Earth. The reason we want to bring those samples back to Earth is because you can't miniaturize everything and send it into space, right? If we're really going to do detailed work on carbon dating or life detection, those samples have to come home. And that is the goal of the Mars Sample Return mission, which later this decade, believe it or not, this decade, we'll have a couple of launches that send a lander and another orbiter to Mars. We'll gather up those samples that Perseverance will place either on the surface or bring to that lander itself, and send those samples up into orbit with a rocket, the first rocket on another planet, a robotic rocket on another planet. And then those samples will be gathered by that orbiter and be returned to Earth. It's a fascinating endeavor scientifically, and from an engineering perspective, it is cutting edge. It's a remarkable mission that we are well on the way to accomplish. And it will answer some of the questions that that are a part of this lecture today, the Are We Alone overall question. Some of that will be addressed by Mars sample return, but not all. Because Mars is a pretty dry place. It's a pretty inhospitable place for life today. We do know that 3.5 to 4 billion years ago it was a much warmer and wetter place, and that life may have gotten a toehold in that time, which is around the same time that life began here on the Earth. Now remember, life is everywhere on the Earth. We used to believe that life could only flourish when there was sunlight. Back before the 70s, that was the prevailing opinion. And it was in the late 70s that we discovered life in the deepest parts of the ocean. Parts of the ocean so deep that sunlight can't penetrate. In those regions, energy was still being provided, but in a different form. It was coming from hydrothermal vents deep in the sea floor. And it's really that revelation that led us to reconsider whether we were looking in the right place for life in our own solar system. Our solar system is home to worlds that are marvelous and intriguing like Mars, but it's also home to a series of ocean worlds, moons typically of Saturn or of Jupiter, but not only, that we know contain vast oceans, oceans larger than the oceans on the Earth. So Europa, Titan, and Enceladus are 3 of these worlds. They're not the only ones, but 3 of the most common targets in what could be an ocean worlds program. Europa has about twice the water volume, more or less, of the Earth's ocean. Titan is full of water deep inside, with about 14 times the volume of the Earth's ocean. And Enceladus is much smaller, but a fascinating world in its own right. And I think that this is the future for answering the question, are we alone in the solar system? The ocean worlds. It's where we should be exploring with technology. It's where we have technology today to go explore. And so the promise of these worlds is there for our understanding. And it may not be me and my generation of engineers and scientists that actually does this exploration. It may be young people in school today, or people online that are just beginning their professional careers that get this opportunity. But believe me, this is an opportunity. We're doing some of it now, though, and so I want to walk through what is happening in this domain with you. Europa, very intriguing world, moon of Jupiter. It is well known to have a volume of ocean beneath an icy crust and above its core. We have a mission today. It's in development, being led at the Jet Propulsion Laboratory, and it's going to launch in 2024, called Europa Clipper, that is going to go out to Europa and do a broad survey with current technology instruments, advancing the Galileo missions, the small amount of science at Europa that came from the Galileo missions that John was referencing earlier. Clipper is going to do a detailed, fundamental survey of this intriguing world to investigate habitability, to investigate whether the conditions on Europa are suitable for life. Will it find life? No, I don't think so. Some people would say it may, and I guess it's possible that it may. But it's not really designed to identify life, but it's a precursor. It's a precursor to do the survey of habitable environments required so that we would know where one day to send another mission. Before I talk about that next mission, let me just say, for those folks around the country working on Europa Clipper, it's a marvelous time because the hardware is finally coming together. The spacecraft is actually being built in real time out at the Jet Propulsion Laboratory in Pasadena, California. And this is just an example, a montage of some of the hardware that's coming together on Europa Clipper. As I mentioned, getting ready for launch in 2024. Now, after Clipper, what happens? We may go to another ocean world first, and that's okay. But eventually, based on the findings of Europa Clipper, we're going to go back to Europa. And we're going to go to the surface. And we're going to touch that surface. We may even bring a melt probe that dives deep into that ice and into that ocean. But we're going to go to that surface because the Europa Clipper results are going to push us in that direction, just like Spirit gave us information that we needed for curiosity and perseverance. Just like Mars Reconnaissance Orbiter at Mars paved the way for landing site certification of future landers, that's what Europa Clipper is going to do for this mission. Now, today we don't have a launch date for this mission. It's not in the NASA budget, but this is a logical follow-on to Europa Clipper, utilizing the reconnaissance and the knowledge that comes from that mission that will be launching in 2024. This is a tough mission, too. Very difficult from a technology standpoint. The radiation environment there is extreme. The surface is much more difficult to land on from a hazards perspective than Mars, so that we need hazard avoidance and landing technology. You don't want to land if you can't get into that ice, very hard ice because of the temperatures out there. So you have drilling and sampling challenges. You have to operate in these very cold temperatures, extreme environment challenges. But these are engineering challenges that we can overcome. And so I believe that we will follow Clipper with the Europa lander mission. But not before we explore Titan. Titan, of the 3 moons, may be the most intriguing. Titan is the second largest moon in our solar system, and it's the only moon to have an atmosphere. Not just any atmosphere, a very thick atmosphere, which makes it easy for us, frankly, to fly through and land, descend and land on a parachute. And in fact, it makes it easy for us to, frankly, fly, which is what we're going to do on Titan. Before I get into that, take a look at these images. This compares Cassini images and Huygens probe images of Titan to the Earth, taken from space or from similar perspectives. If I didn't have the words on there for the columns, would you be able to tell the difference? Titan is a very Earth-like world. It's a world with a thick atmosphere. It's a world with liquid cycling from the atmosphere down to the surface and then back up, much like the rains do here. It's a world where liquid flows across the surface in rivers and lakes. Of course, it's very, very cold, so you're talking about methane and ethane largely. But it is a very Earth-like world, and it's one that has for us the best example of prebiotic chemistry. So we have on Titan this thick atmosphere where photochemical reactions are taking place, and these organics are literally raining down on the surface. They're being modified across the surface from the interaction with the surface itself. There's an ice, a water ice crust, and beneath that ice is a deep subsurface ocean. Okay? Who wouldn't want to go to Titan? I would. And so the questions that we have of Titan include things like, what types of organics are formed in the atmosphere, how they get modified with interactions of the surface, and do they actually transport down into the subsurface ocean? Is there mixing? And what does that portend for life potentially in that ocean? Of all the worlds in our solar system, Titan is a singular destination for understanding the chemical processes on our own world that led to life, led to the development of life. So if you want to go back in time and study prebiotic chemistry that led to the creation of life on the Earth, you must go to Titan. Now, fortunately, we're going. And we're going with a mission called Dragonfly that's going to be launching in about 2027. Now, Titan is much harder to reach, just like Europa is hard to reach. Titan is much harder to reach than Mars. But we can get there with a large launch vehicle and a multi-year trajectory around the sun, doing a direct entry just like we do at Mars, at Titan, slowing down with an aeroshell, opening up a parachute, and then descending ever so gradually through that thick atmosphere. Instead of the 7 minutes of terror that you may remember from your Mars entry, descent, and landing days, we have 2 hours of terror here. It's not quite as dramatic, but there's still a lot of things that have to go right. And then one could land, or since we have a thick atmosphere, one could fly right out of that back shell with a quadcopter. And in fact, that's what we're going to do. We're going to have a mobile lander that, instead of having wheels for mobility, has blades and actually lifts off and flies from one site to another, doing scientific observations over a much broader range than a rover could traverse. And here's just a brief video of that. Dragonfly coming down on its parachute after the descent, the quadcopter being released, and flying across an animated Titan surface to its first landing site. It's taking imagery, by the way, during this flight of where it would go on the next flight. So we don't have overhead orbiters to give us a great view of the entire surface of Titan. And so this system has to actually identify its landing sites either in real time or from a subsequent flight. So it would do science on the surface, and then off it goes to the next site. And over the course of many years, 3 years of science observations, we believe that that system can traverse not a kilometer or two, not 10 kilometers like we might get out of a rover on Mars, but a couple hundred kilometers across the Titan surface. And in doing so, we'll be able to sample a range of geologic units, as shown on this slide. Everything from sand to dunes to ejecta to the very shoreline, if you will, of the ethane-methane lakes. Now we're going to have to fly up and over those dunes, and this is not a mission without risk. But this is a mission that NASA's currently planning to do in the 2027 time frame. So 5 years from now, this mission will be launching. It's remarkable when you think about it. The other body that I wanted to mention briefly is Enceladus. And there are no missions presently on the books in the next 5 or so years to go to Enceladus. But boy, this moon of Saturn is compelling. So these are Cassini images. That's a video that was made by the Cassini spacecraft of Enceladus. And you see that whitish plume coming out of the bottom? That's water, just being pushed out into space. That's water that one could sample just by flying through it. And the prevailing theory is that that's not only water, but coming up from these hydrothermal vents deep within Enceladus is both water and organic material. And so one could sample the organics of Enceladus with a flyby, or by landing very close to these jets and just having it rain down on you. Right? It's a remarkable world, and there's been a number of studies, very intriguing studies, for how we should explore Enceladus. I believe we will explore Enceladus soon. In fact, in the most recent Planetary Science and Astrobiology Decadal Survey, one of the larger missions, called flagship missions, that was put forward as a priority was called the Enceladus Orbilander. This is a concept to send both an orbiter and a lander together, like we used to do in the Viking days, to Enceladus. The orbiter would do, obviously, orbital observations and reconnaissance. The lander would go down on the surface and basically get rained on by organic material and study that material. In the timing of the Decadal Survey, this is a mission that's out towards the end of the decade, so maybe the end of the 2020s or Perhaps even in the early 2030s is when this mission is scheduled to go, but it's in the planning stages now. And what a remarkable mission to be a part of and to consider the development of. Full of technology challenges and clearly going to answer some big scientific questions as well. Now there's a couple other elements of this quest that I wanted to just briefly mention. There's another mission to Uranus that you might not think is tied to the answering the question, are we alone? But frankly, I think it is. And then there's exoplanets that I want to talk about also. So the number one priority in the most recent Planetary Science and Astrobiology Decadal Survey was the Uranus Orbiter and Probe mission. Uranus is one of the two ice giants in our solar system, along with Neptune. And despite this image of Uranus, which came from one of the Voyager spacecraft, makes it appear that it's kind of a light blue, blobby kind of planet, not much detail there. In reality, Uranus is complex and fascinating. If you take a look at the lower part of the left-hand side, you can see why. There's an atmosphere, there's interior, there's rings and moons, there's all kinds of complexity, and we know almost nothing about Uranus. We had a flyby, sure, but the ice giants, Uranus and Neptune, are the only class of planet in our solar system to not have had a dedicated explorer. What's worse is the ice giants are the most common extrasolar planet in the universe, in the galaxy. And they're the missing link in our understanding of how planets form. It's almost unconscionable that we haven't been to one of the ice giants with a dedicated mission. Now, fortunately, NASA is planning to fix that. As I mentioned, this was the top priority in the Planetary and Astrobiology Decadal Survey, and NASA is currently considering plans for a new start of the Uranus Orbiter and Probe sometime in the next few years, and this mission would probably launch later in the 2020s. But some of the questions that we would ask are just very basic questions about planetary geology. What's it made of? Is it largely ice? Is it largely rock? Is it fully or partially differentiated? The Uranus moons actually have some astrobiological potential. There could be a couple of ocean worlds in the Uranus system that we're just not even aware of yet. That would have, ocean worlds means a world with a lot of water, right? That would tell us about how far water can extend beyond the sun and still be in a liquid form. That would be a pretty fascinating result, both for our own knowledge here in the solar system, but also to understand worlds around other stars. Because once again, Uranus and Neptune are the type of planet that we see most often when we identify extrasolar planets. So as I mentioned, this flagship mission has a number of reasons for having its high priority, but its astrobiological potential is certainly one of them. And I think that when this mission occurs, we're going to take a good step forward in our understanding of life in the solar system. I didn't want to leave this topic without talking briefly about exoplanets. What I'm showing on this video here is actually my favorite display at the Jet Propulsion Laboratory. When I would go to work there, I used to take images of this display because I remember visiting when I was a professor at Georgia Tech or when I was working at NASA Langley, and it would say there are 1 or 2 extrasolar planets. And then look at that counter. We're over 5,000 now, right? It's remarkable. So Earth-like exoplanets, right? We now know, remember I told you earlier, when we took that picture of the pale blue dot of our world from Neptune's orbit, just past Neptune's orbit, our world was one of just 9 planets. Now we know of over 5,000 planets in the night sky. And it's through advancement in telescopes that we're able to learn more and more. In fact, I believe that as time goes on and our telescopes get better and better, the definition of an Earth-like planet will also evolve. So today we refer to Earth-like worlds as a world that is at about the right distance from its star, so that it's about the right temperature relative to the Earth, plus or minus a little bit. Pretty soon, I think we'll be talking about such worlds that also have atmospheres made of largely nitrogen with perhaps a little bit of oxygen. A decade later, we'll be looking for trace pollutants in those atmospheres. Just kidding, but maybe not. So how are we doing this? Well, the image in the middle there is a very recent data point returned from the James Webb Space Telescope. So James Webb is already on this case. In fact, this is measurements of planet B in the WASP-96 system that demonstrated the presence of water vapor in the atmosphere of that planet. Water vapor consistent with clouds or haze. And this is a planet that's more than 1,000 light years away. Right? Webb did that just a few months ago. We're about to fly the Roman telescope, and along with it, there's a coronagraph that's being developed. The coronagraph is another way of shielding the light from the host star so that we can focus on the much fainter planets that are orbiting that star. And when Roman flies with this coronagraph, we should be able to directly image, not just measure the light change, but directly image planets around stars that are almost 1 billion times fainter than their host stars. Boy, what'll that tell us? I think it's going to tell us quite a bit. In particular, when Roman and its coronagraph are flying alongside, basically, or at the same time, as JWST, the James Webb Space Telescope, we'll be able to use these assets together to really zero in on this question. Now we have coronagraphs and other types of occulters, deployable and thin film structures. For those of you in engineering that want to support this cause, the hunt for exoplanets is enabled by a whole host of technology, just like the Mars program was enabled, or is enabled, by landing mobility and sampling systems. It's investments in those technologies that are making all of this possible, that are allowing us to learn more and more about worlds around other stars, and in particular, Earth-like planets around other stars. So I'm going to come back to where I started, which is the field of astrobiology. It's a growing field. It's a field whose potential is really just beginning to be unleashed. There are more and more scientists every day going into this field, and frankly, what they need are engineering partners to develop the technologies and the systems to push ocean world exploration forward, or to push Earth-type exoplanet identification and knowledge forward. The coming decade is going to have a number of significant advances in this field. We're going to do Dragonfly at Titan. We're going to do Europa Clipper at Europa. We've got flagship missions planned for Uranus and Enceladus. I think we'll actually figure out a way to get to Enceladus with a lower cost mission at some point in the coming decade. The exploration of the ocean worlds is there for the taking. We have the technology in hand. We are growing the scientific knowledge and our scientific questions. And so it's really just a matter of focus and building out a systematic approach to exploration of the ocean worlds, much like the systematic approach that has been so successful for us for so long at Mars. Not only is that our best hope, in my view, of identifying not just habitable environments, but other life forms in our solar system, but the knowledge gained will also inform and constrain the search and the definition of Earth-like planets around other stars. So I, for one, would love to be a part of this quest, love to keep pushing this forward, but I also know that this is a quest that, will take 10, maybe 20, could be even 30 years. And so what excites me the most is knowing that the young people in our universities today, or just beginning their careers in this field, are going to get to accomplish this. I can't wait to see what they're able to do. I can't wait to see what we learn and create together. And with that, I'll pause and see if you have any questions. Thank you very much. What's that?
Would you tell people just to line up at the mics that they...
Al says if you have a question, go to the mic. There's mics in the aisles.
I have a question about two artifacts. Aren't we confident that life originated around the deep sea thermal vents and not just settled life that originated in sunlight, just didn't settle down there and found alternate food? Because if we're basing missions on going around looking for thermal vents, it seems like we should be very sure that the thermal vents are actually the source of the life. And it would seem like DNA should tell us that. I mean, are there, those little beasties down there, sufficiently DNA different from everything else that's been spawned in sunlight that we're confident of that? That's the first artifact. The second artifact is, well, most of the planets are icy giants. Well, icy giants are the ones easiest to see. They're the big, bright objects. Are we confident we're just not? Yeah, I would readily accept that most of the things we see are icy giants, but do we have any confidence that's really the case with the most exoplanets? Or is it just an artifact of our observation?
Yeah, so let me take the second one first. So yeah, I may have said it a little incorrectly. I meant to say that icy giants are of the more than 5,000 extrasolar planets, the largest percentage of them are ice giants, right? That's what I was trying to say.
Well, that's not surprising, because
Sure.
they're the brightest.
Well, they're the brightest, but they're also, sure. I mean, they're not the largest, right?
But they're the biggest, they're the brightest.
I got you.
What we see is brightness. We don't see,
you-
if it's dark, we can't see it.
You see both. You see basically from the drop in sunlight, right? Or drop in starlight.
That's a great, okay.
Yeah, so you see both. In terms of your second question about life in the deep sea vents, that's not my specialty, just to be clear. But what I was trying to say is that we know that life exists around the deep sea vents, where sunlight is not the prevailing source of energy. And so that.
Hold on.
Go ahead.
Yeah.
I didn't say it was different life. I said it was life.
Okay,
So-
life that exists in a deep sea vent extraterrestrially has to originate there without sunlight.
Sure, just like life on the surface has to originate
Well,
with
but
sunlight.
life on the surface could have very well, and probably did originate with sunlight, and then sank.
That's unknown. I don't know.
Well,
I don't know why would it. It has to not just move from one environment to another. It has to thrive, right? To continue.
live.
Yeah, it has to live and thrive.
getting started seems to be the big bitch here.
Agree.
It's like get started, it goes for it, but getting it off the ground seems to be the hard part. If we're going to look for thermal vents that have never seen sunlight, we should have some confidence that you can kick off life in a thermal vent.
I guess what I was trying to say, let me pose it one different way. That we believe that life requires water and energy, right? And that energy can come in one of many ways, right? And we now have multiple ways here on our own Earth for the source of that energy.
Okay, but
Think
the
about it that
premise
way.
says all energy has or at least has an equal likelihood of spawning life. That may be true, but that's not clear.
Sure. It doesn't have to have an equal probability, sure. I'll agree with you on that. We should talk about this more, though. This is fascinating. Thank you. Lance.
Dr. Braun, thank you. I share your enthusiasm for the search for life and your focus on the moons of Jupiter. And I'm also struck by your point that we've made progress in terms of our planetary probe vehicles. You know, we started with kind of stationary, we put some wheels on them, now we're flying them, we're doing, but I was hoping you would share a little more. What I didn't see is you hinted at the underwater approach, and I didn't see the blueprints or the discussion of the underwater autonomous vehicle, or so when you bump into the Norwal, we'll get a good picture of it. So maybe you could just share a little bit, if you're willing to.
Sure. So, I mean, there are concepts that people, but they're really just concepts at this point because the missions are pretty far forward in time. But for instance, at Europa, where I showed a concept of a lander, but there are concepts for submarines, if you will, or autonomous vehicles that would either melt their way down through the ice or be placed down through the ice, depending on the thickness of that ice, and do exploration in the oceans of Europa. You could imagine that on other worlds as well. We're, several decades away from having even the opportunity to do that, but I think that opportunity is there. And if you look at, autonomous underwater vehicles here on the Earth, their capabilities are just rapidly expanding, right? So, just like you're seeing drone flight on Mars with Ingenuity at first, and now perhaps in the future with Dragonfly, I think autonomous underwater vehicles would certainly play a role here.
All right, thank you. Yeah, I'm just fascinated by this because, as you said, there's new discoveries now in terms of our technology here, and if we're looking for life, I think your best chance is down in the water, but you got to get through some ice crusts as well.
You got to get there. Now, there are plumes. There are plumes in all of these places, and so, and there is pressure, and so an alternate approach, if the ice is too thick, for example, an alternate approach is to go near one of these plumes and wait to get rained on.
Thank you.
Yes, I had a question about the ice giant orbiters. I was actually reviewing a NASA proposal several years ago, or reading about it, that of a Neptune orbiter. But the problem with the Cassini probe was it had to consume half its fuel in order to break into Saturn's orbit. Were they planning to use the same process for a possible Uranus orbiter, or were they planning to use aerobraking, which has its own uncertainties?
Yeah, well, so there's different concepts. I think the concept that was in the decadal survey was what you call a direct concept. So it was a chemical propulsion, no aerobraking or aero capture, with an MMRTG for power source, and to do the science mission. But there are other ways to go, and you could, for instance, try to fly through the atmosphere. But given that we haven't had a dedicated mission to Uranus or to Neptune, there's a lot of uncertainty in that atmosphere as well.
The other interesting thing about Uranus and Neptune is they have really odd magnetic fields that also
Yeah,
need
they
to be
do.
studied.
Yeah, particularly Uranus, right, with its 98-degree tilt. Absolutely. Thank you.
Take my place in line. The Indian government just recently declared end of life on their Mars orbiter. And it triggers the thought, are there lessons to be learned for the extremely low-cost, high-gain mission that they conducted? And how does that compare, perhaps, to like SpaceX's experience for launch costs as well? And are there things we can learn that will give you that much more to play with for the experiments that we think need to be done?
Yeah, well, that's a great question. Thanks. So, the Indian Space Agency mission was an extremely low-cost mission. The UAE mission was also pretty low cost. You got to remember, in each case, it was their first exploration of Mars, right? And so when you're on your first mission, you're going after some pretty general scientific objectives. It's a little bit easier to keep the cost down on something like that. Once you do that mission, you're going after more detailed and then more detailed still science. It tends to push the cost up of the missions. In terms of launch vehicles, though, let me just point out, one of the reasons that the Mars program has been so successful is that it started with a marriage to the Boeing Delta II. And so all the early launches were on these smaller, low-cost launch vehicles. And now the missions are bigger, and so they're on bigger launch vehicles, except there are companies like SpaceX and Blue Origin soon and others that are now proposing low-cost launch systems for big things. That's really going to help us for ocean worlds because, frankly, the cost of a Falcon 9 is cheaper than what we were paying for the Delta II, all those years ago. And the Falcon 9 or the Falcon 9 Heavy and variants by other companies have the capability to go regularly to the ocean worlds. Now, it's regular trips to Mars that have what enabled the continuous exploration strategy of Mars exploration. And so what we need is, and what we have today, are these low-cost launch systems that could enable ocean world exploration. Thanks. Go ahead.
Thank you very much for your very interesting presentation. For making the next step, you need, of course, new tools, new instruments, and can you elaborate a bit on what would be the thing which would bring us a big step forward in the missions? From an engineering and instrumental,
from an engineering standpoint, or from so there's not just one thing, unfortunately. From an engineering standpoint, I think precision landing technology and hazard avoidance, being able to land where you want to land and safely do so, particularly on a place like Europa, for example, is pretty important. From an instrumentation standpoint, there have been some real advances in mass spectroscopy, and that is kind of it's not the only instrument, but it is a go-to instrument for some of the sample analysis kinds of measurements that I'm talking about, needing to make at places like Europa or Enceladus. Okay, thank you.
First of all, thank you very much for this super inspiring and great talk. I've definitely learned a lot. So I saw that you guys are sending a Dragonfly, so a drone, to Titan. And I also know that one of the biggest challenges of the Martian helicopter was the thin atmosphere, whereas Dragonfly is being sent to Titan, which I believe has a thicker atmosphere than the Earth. I was wondering, what are the sets of challenges with sending something to a thicker atmosphere rather than a thinner atmosphere? I'm assuming it's a bit easier, but I don't know. That's, I guess, a question, which leads me to the other one, is that I looked at the body shape itself. I don't know if that's, I guess it's not super aerodynamic. Is that because you don't need that, or is that because of weight constraints? Yeah.
Well, that's a great set of questions, and I'll cover what I can here, and we could talk more later also. The challenge for Ingenuity on Mars, as you elucidated, was basically flight. I mean, it was like flying at 100,000 feet here on the Earth, right? Nothing flies at 100,000 feet here on the Earth. And so actually having a system that could function, be light enough, and then the rotor system to actually do that flight, that was the true challenge, given Reynolds number constraints of the rotor itself. On Titan, it's a very different set of challenges. We have a very thick atmosphere. It's almost like flying your drone in water, if you will. It's that thick of an atmosphere. And the real challenge is not lift per se, but just temperature. So Titan is exceedingly cold, and so the materials that you have at your disposal are somewhat limited. In addition, Dragonfly is a very large system. That system is basically the size of the Perseverance rover, but it's flying, right? So it's the size of a small car, okay? And so, you know, making something, you know, operate in those extreme environment temperatures and making something of that size fly, you know, is the real challenge there. Because there are limits, basically, for something that big, then your rotors get limited, and then it all has to package inside the same size aeroshell, because that's limited by the launch vehicle, right? So there are some fundamental geometric constraints, and yet you're trying to take all this mass. So that's the real challenge. Okay? All right. Maybe last one? Go ahead.
I have another question.
Yes, sir?
With the increasing distances from Earth of these landers, will the pros have to use artificial intelligence and machine learning to make their own decisions about landing in real time?
Well, so they already do. So yeah, our systems, you know, we're not joysticking any of these systems. The systems have to have their own smarts, basically their own autonomy. That's true at Mars, you know, where the one-way light time is anywhere from, you know, 7 to 19 minutes. That's true certainly the farther out you go. And so, yeah, all of these systems are designed to basically receive commands from the Earth about, let's say, the next day or the next several days, and then execute the sequence of events autonomously, you know, on their own. So that's whether the sequence of events involves traveling or flying somewhere or doing science or communicating to the Earth, you know, regardless of that, that's all done autonomously by the system, you know, based on what we send it the day before. Okay? All right. So thank you all very much. I appreciate your time here today.
Don't go away yet.
No? All right.
I just asked him not to go away yet. You know, there are a lot more questions that really could be asked. The question you asked, are we alone? What's the answer? Is it yes or is it no? Or is it maybe?
What do you think, John?
Well,
I'll tell you what I
think. Get a
think.
whole other discussion going, but if you say, what are we alone, what do we mean by that? Mm-hmm. Is there life anywhere else in our solar system?
You and I are together.
Or is there, or is there life anywhere else in the universe? And there's a lot of arguments that, and I don't care which way you go, that somewhere else there's life. Whether it was spontaneously created or came from Earth and fell to the bottom of the ocean and developed from there, or created by God. But whatever approach you take, if you think about it, I think the answer has to be yes. And the way I think about it is strictly in terms of numbers. He showed you a picture with a sky full of stars. People have made a good faith estimate to try and understand or guess or estimate what are the total number of stars in the universe. And it's a hard number to count, you know, and so people, well, let's say each star was the size of a grain of sand. Then how many grains of sand would represent the number of stars in the universe? And the answer comes out to be, since there's billions of galaxies, 200 to 600 stars in our galaxy, and maybe a like number of galaxies, you multiply those two numbers together, and the answer you get, in terms of grains of sand, there are more stars in the universe than there are grains of sand in all the beaches of the world. That's a lot of grains of sand, and many of those grains of sand have planets. So if it's just a probabilistic thing that life had just required the right combinations of soup or whatever it was, that it must have happened more than once. And if God did it, why would he pick one crummy star out of one crummy
Good point.
galaxy in the universe? So the answer is no, we're not alone.
That's right.
The question is there any life accessible to us?
There you go.
And the answer to that is probably no.
Except in the ocean worlds.
Pardon?
Except in the ocean worlds.
Except in the ocean worlds. Okay.
There we go.
Well, this is a great discussion. But we're going to conclude it with presenting you with a
Wow.
this little token of our gratitude for what you've done here. I think it's a wonderful talk. It's a lot of questions that probably will never get answered in your lifetime, and not mine, because I've only got a few more years left, according to my financial advisors. Everybody has to die when they run out of. Oh, okay.
He wants us to move over here.
Say, Al, why don't you come up here and help me with this? The Brill Lectureship is a joint award presented by the NAE and the AIAA.
Why don't you take off your badge, John?
Want me to take off my badge? Okay, I just took off my badge. Now, so I'm going to represent the NAE, and you're going to represent the AIAA.
We can do that.
So Bobby, come and stand in the middle.
I think so.
So congratulations, and thank you so much.
Thank you.
Okay.
Thank you.
Thank you.
Thanks, Al.
Congratulations.
Thank you.
You're gonna hang around for a while, right?
Yeah. Thank you.
Who's going to carry this plaque off?
I got it.
Okay, good. I don't trust myself.
Now that you live nearby, we don't have to pay to ship it.
That's true. Thank you all very much.
Thank you.
Hmm.